So today we're going to be showing how the hybridization of a tribromoethylene molecule shares its electrons and how it all works, how the valence electrons come into play, how the orbital structures show how it hybridizes, and at the end how the contour diagram would show for each atom. First off, to begin with, we will be doing the Lewis structure of this molecule. Lewis structure. So what we have here, we have 4 bromine atoms, each with 7 valence electrons, so 7 times 4, and 2 carbon atoms, each with 4 valence electrons, so that's 4 electrons times 2. Total up to 36 electrons. It's best to start with the Lewis structure just to better understand how the molecule is. However, the Lewis structure does not fully explain how these atoms are bonded, or how these molecules bond with outer molecules. Since it's so limited to a 2D dimension, it doesn't fully explain that. It doesn't fully show the geometry of this molecule. So drawing it out is to better get in the diagram right here. So C double bond Br on each carbon right here. And we'll go ahead and draw the valence electrons on each bromine. Don't want to forget those. So this shows us the Lewis structure of a tribromoethylene molecule. Now this only helps us to get closer to the Vesper diagram, which is much more explanatory than the Lewis structure. So if we move a bit down here, we'll write Vesper. So Vesper is kind of a 3-dimensional molecule diagram, which helps us better, of course, understand how these molecules or atoms within the molecule bond together, what angles they form, how their electron and molecular geometry form together. So in reality, we'll consider one of these carbon atoms as a central atom. So we'll go ahead and draw that C right here, double bonded with another C. Now, our own reference would be considering 1 carbon. With 1 carbon, we would then be able to better see out the geometry of the molecule type. So not necessarily the molecule, rather the end of the molecule. So let's just finish off these BRs right here. Now, the carbon has 3 electron groups, considering the double bond to be 1, a bond with the Br, and another bond with a Br. So 1 electron group right here, another right here, and considering these 2 over here, 1 right here. Now, after drawing those out, we would then kind of mark out the equilateral triangle we have over here. A 3 electron group central atom means we have a trigonal planar electron geometry. Now, looking over here, not only do we have the same electron geometry, we have all 3 atoms occupying those electron openings, we could say. So since the electron geometry is the same as the molecular geometry, we would then also consider the molecular geometry to be a trigonal planar as well. Trigonal planar. Now, normally, as a reference, we take a look at the ammonia molecule. In the ammonia molecule, it also has 3 electron groups. It has an angle of 120 between them, since it is very, very non-polar. It is very symmetrical, you could say. it has approximately 120 degrees around between each bonding atom. However, here it's pretty close, but since there are different electronegativities, such as the double bond, the bromine atoms, we can just take it as a reference and put approximately 120. Might be less, might be more, depending on the electronegativity in each case. Approximately 120. Now, to better understand this, using a molecular structure kit, we could actually kind of make this structure using the ball and sticks in the structure kit to actually understand how this works. So, placing this here, we could visualize these two double bonds right here. So the double bonds, we have each red one is a bromine atom and our carbon atoms in the middle. So this is to better understand how these bond in real life in three-dimensional shape. We could actually take a look at these, better understand it. Now, through the Vesper method, it is also much easier for us to actually, let's see here, space that there. We could then actually draw out the hybridization to actually show how these atoms share their electrons and bond together. Now, we would start off with the central atom being carbon in this case. We'll draw out the carbon, so we'll start with the ground state carbon, and start with the 2s and 2p. A carbon has 4 valence electrons, so we'd fill the first 2s both, then add 1 electron to each orbital over here. Now what we want is, so if we take a look at the Vesper structure that we did previously, we actually have four electron groups. Well, 3 electron groups actually, but considering it as 4 parking spots because there's a double bond. That double bond, we consider it as one electron group. So what we do here is we actually want an extra electron here. Now where we would get that is actually from the 2s orbital right over here. How that would happen is by promoting the electron. Promoting the electron means adding any source of energy that would actually bump that carbon atom, making from a ground state, well, bumping that electron from the ground state carbon, actually forming an excited carbon, which is an excited state carbon, which would be C aster right here. So what would happen is that this electron will be promoted electron. So we would then have 2s and then 2p, and this promoted one would actually go over here. So then we would have 4 lone electrons, not lone pairs, lone electrons, which are then capable of bonding and sharing their electrons with other atoms around. Moving over to the side, so let's see here. So from this excited state, the atom would undergo what's called a hybridization. This hybridization would actually kind of combine two orbital shells, in this case being the s and the p, to form a bigger shell which is capable of sharing electrons from an sp shell of this atom, the carbon atom in this case, the excited carbon, to another carbon or another bromine or whatever it is that it needs to share an electron with. So in this case, what we actually need is 1 and 2, 3. So we're going to be sharing, since we have a double bond. In the double bond, one of the bonds is considered a sigma bond and a pi bond. However, with the bonds with the bromine, those are also sigma bonds. Those sigma bonds would actually be these 3 right here. A sigma bond is a shared electron between almost any different orbital shell, and being sp, pns, pnsp, anything. But having a pi bond, which is that second bond of the double bond, that is a shared electron strictly between two p orbital shells. So what we need, we still want to keep one p shell, not hybridize that. We only want to hybridize these three. So what we would do is actually hybridize this right here, hybridize, and then we would get what we call a hybridized sp2. This would be 1, 2, and 3. Now what we would have here is also that p shell, that 2p that we did not hybridize, and that would be over here. Let's see here. Now with the orbital notations of the Br that we had, the Br does not undergo hybridization. It is fine as it is. So taking a look at its valence ones, we see that at its 4p. So let's just move this down here. Actually make it a little bit smaller. I guess not. And we will write 4p orbitals, filling each one with 7 valence, well, it's a total of 7 valence electrons, one after the other. And what we can do is actually duplicate this right here and move them side to side. Alright, and what then happened, so this one would be the first bonded state C, while at the meantime, what other thing happens is we actually get another bonded state C. So what would happen here is getting another sp2, this is other C, and a 2p as well because it undergoes hybridization. And looking at the other bromine atoms that attach to the other C, so we can go ahead and duplicate that, move that down there, and duplicate it once more to move that down there. So in reality what actually happens is this lone electron right here actually is shared with the sp2 of the first carbon. This one right here shares with this sp2 orbital right here. And same thing for the other carbon. We have one over here, and we have the other over here. Now, one electron from the sp2 of the first carbon and the second would also share. So we'll actually get those there. Having these here as well. These are all sigma bonds. So we have a total of 5 sigma bonds. While, like I said, a pi bond is strictly between 2 p shells. It's just between those two. So these two would actually be sharing, forming that pi bond, and this is actually the second bond in the double bond, which is the pi bond. Now then, zooming out and going down, this would better let us visualize the contour diagram and how these atoms actually bond together, how they actually share these electrons. So contour diagram. Let's actually zoom in right here. Let's draw a straight line. At least try to. And we would then be able to work on this leveled line. Alright, so now what we would be able to do is draw the carbon, first carbon, the second carbon. We'd also need to draw the lineouts for the bromine as well, which would attach from the top. You do that in a bit. These here, and these here. And since we have P shells, which is the pi bonds, I like to relate them as dash just to kind of line up that, maybe not forget about it. So we can now draw out the sp2 for each carbon. So probably like that. sp2. Then draw the other sp2 for the carbon over here. And this is our first sigma bond. Now moving on to the sides, we have another sp2 over here. You want to try your best to draw them relatively the same size. sp2, these are the shared electrons. Now, bromine will be sharing these two electrons with its p shell. So p shell is kind of different to draw. So you actually go like this. The line going in, that will be the first Br. We have our second sp2 here, and over here we have our other p. Now the third 3p is relatively bigger than the sp, but in this case we could draw them out almost the same. So that's a pi, that's a sigma and sigma. Zooming out to the other carbon, we also have another sp2 right here. Zoom out over here. Electrons here. This is also sp2. This is Br. This is the P, 4p actually. P for Br. 4p and 4p over here. Now last but not least, we have the pi bonds that we need to illustrate. So let's draw that out here. The pi bond is kind of as that thin balloon shape. The p, sorry, the p orbital for the carbon, because this is what overlaps. These overlaps are going to actually form that pi bond that we have. So we're going to have one electron here, one electron here, and these would actually overlap such a way that we actually form the pi bond over here. So this contour diagram actually shows the overlaps and how these electrons are actually shared. Very different from what the Lewis dot structure would actually show. We can actually see that the 4p orbital of the bromine, how it actually overlaps with the sp2 hybridized orbital of the carbon, which also has 3. So it'll be 5 sigma bonds. We have one over here, over here, over here, over here, and over here. Of course, our double bond, which meaning we have 1 sigma and 1 pi bond. These two would be relatively the same. Now, also using another app, we can actually see that, inserting the picture here, in the application, it actually seems the same right here. We could see that over here we have the 2 pi bonds, these red ones, long red ones. We have the p orbital of the bromine on each end, sp2 for each carbon, and the inner sp2, the sigma bonds, of course, with the both carbons as well. So this is the contour diagram of tribromoethylene.